Welcome and good evening. And tonight we want to continue on our quest to learn how to code in MS-DOS. This time, this is not specific for MS-DOS, but a lot of you guys have asked if I'm going to do another game, and I think that's a good idea. But this will be much more complex than the little Pong game that we did in the first few episodes. So we need to work our way towards that goal. And one of the stepping stones here is tonight to actually be able to load some external pictures, because last time we did all the graphics only by programming C code. And of course that's not very convenient. It's much nicer if you can paint some nice pictures in your favorite paint program, export them and then load them into your game. And the easiest way to do that is basically just dump the pixels into palette data, and that's it. But that will take quite a bit of space on the disk, and since we're doing MS-DOS here, and I personally am targeting very old machines, maybe even XTs, but definitely 286 and 386 processors, we want to be efficient space and CPU-wise. So today we want to learn how to load GIF files. I think everybody of you knows what GIF files are. They are pretty popular still today as a means of displaying animated thingies in all kinds of programs on the web, in chat programs and whatever. Most of the time nowadays they are actually not GIFs anymore, but something like MPEG-4. But yeah, who cares? Their origin is actually from the mid to late 80s. Originally, the format, which actually stands for Graphics Interchange Format, was done by CompuServe, who some people may still remember. It was one of the early providers for online services, even in the time before mainstream internet. And it was pretty proprietary. Later, they were basically just an internet service provider. And I think they got bought up, maybe from AOL, I don't know. But they went under. They were never that popular over here in Germany, but I think they were pretty big in the US anyway. So on the World Wide Web organization forum, you can find the actual GIF specification, because every web browser basically supports that. And we will have a few looks at this maybe in between. But since this will be, again, a long episode, I'm trying to concentrate on the most important things. I will talk a little bit about the compression in a short while, but first let's look at the program. I've already prepared a bunch of things. I prepared the GIF header file, which we'll take a look at soon, and I reused our VGA routines from the earlier episodes, and I wrote a very small program. The VGA routines now have a C struct called image, which just takes the raw image data, a palette, and also the size, like 320 by 200. And yeah, our GIF header file defines a load GIF function where you just pass a file name, and if it was successful, it will return a pointer to an image structure, which is not null. So if it's not null, we're fine. Then we switch to graphics mode. We set the palette that was supplied by the image, and then we copy the data from memory to the VGA card. And this program is very, very hard-coded. It only supports 320 by 200 pixel GIF files. And it's GIF and not GIF, obviously. Then we wait for key press, return to text mode, and that's it. Pretty straightforward. So why did I choose GIF? Well, we could just simply load bitmaps, Windows bitmaps, which are very simple, almost pure data. We could use PCX, which is a very fast and very simple compression algorithm, but it doesn't compress dithered or more complex pictures very well. GIF has a pretty advanced compression algorithm compared to the other two. But it doesn't work well on photographs, So although I use the photograph as a text picture, it will not compress very well. But like Lzw and hand-drawn pictures for games usually compress very well. So you can see a lot of space efficiency here. The algorithm that I'm using, I simply took from this webpage here, and it's a very nice page for DOS coders. I will link to it in the description. I also used their Sound Blaster code as a starting point, and when you compare my source and their source, it still looks pretty similar. The same is here true for the GIF loader. I left it mostly untouched. I tried to refactor it a bit to collect all the global state into one decoder object or decoder structure, which you will see in a minute or two. And to make it possible that you have multiple decoders running at the same time, probably not on a DOS, but we could probably salvage this for other platforms as well. There's still a lot to do. The decoder that we have here is pretty slow. The DOS box here simulates with 3000 cycles. That's roughly somewhere between a 286 and 386, and also tested it on my real 386 machine, and this test file loads in a couple of seconds, and that's pretty slow still. So in some further episode we might want to optimize this, but for now it's good to have it in a simple fashion, because otherwise you won't understand it. Probably. This will be already a lot to take in. The GIF file uses the so-called Lzw Compression Algorithm. That stands for Lzw, which is the authors of the paper published in 1984. And it's a interesting compression algorithm which uses varying lengths of code words to encode the whole file. And there's a very nice example on the Wikipedia page. Usually with those algorithms you would need to store a dictionary with all the words that are contained in one document, be it a picture, so the sequence of pixels, or a text document. But that would of course take a lot of storage, so you don't do that, but you progressively reconstruct the dictionary as you go. The initial dictionary that you have is basically just the whole ASCII set. The example here on Wikipedia is just the 26 uppercase letters encoded with 5 bits, because that's what you need for 26 letters. But in reality we will use 255 or 256 bytes. We know those implicitly, obviously, and we will reconstruct the rest of the dictionary as we go. And as an example, they use here the string to be or not to be, or to be or not. And this is quite a bit of repetition, so we would assume that strings like to would be compressed later, again represented not by 2 characters but by less than is necessary for 2 character bits. And yeah, let's see how they do that. So basically we always have a current sequence, longest sequence that we know from the dictionary. We have the next character that's coming from our stream. We have an output code. This is our encoding basically, and the bits. This is just the binary representation. And then we will emit also possibly a new dictionary code to enhance our dictionary on the fly. So at the beginning we don't have any sequence, so we start off with null. The next character is a T, and nothing has to be done. So we take this as our current sequence, the T, read the next character, and we say, okay, we have T and O. We don't have a code for TO yet, but we know that we can output the 20, because T is in our current dictionary. And we will need to use a new code. We need to invent a new code for the sequence TO, because that's a new sequence that we saw, and we already have 26 codes in our alphabet, so 27 is now reserved for the TO. This is how the encoder works. The decoder would do basically the same. It would encounter the 26, would do the lookup and see, the next character that is encoded is also already known. It's a 15. So I know that from the 27 and the 15 I have to from the 20 and the 15 I have to reconstruct the new entry 27. So from now on, whenever we see the TO, we will use the code 27. Let's look down here. Here is a recurrence of the exact thing happening. So the current sequence is TO here. First we encountered the T in the next character here. And after the T we found, okay, we already know that. So we have TO and we will emit the 27. But it will be followed by the B, and if we went through all this, we would have found, okay, we don't know yet the sequence TOB, so we emit another new code. And you can see here the codes are always increasing, 27, 28, and so on to 36. And the longer this sequence runs, and the longer the input data will be, the more compression you can achieve actually, because every time you see a sequence for the first time, you have a very inefficient code. The second time around, you will have a more efficient code. And the codes grow gradually. As you can see, we start off with the T, then with TO, which is emitted, then with TOB, and then TOBE. This is the longest word in our dictionary that we will find. So the words can get very long, and this will of course then mean that we have a very efficient compression if the sequence reoccurs at some point in the text. The same algorithm can be applied to the GIF file basically. So here's again the example being decoded. I won't do that now because this will take too long. I will explain a bit more about the algorithm as we go implementing it. Okay, so first of all, I tried to code this from scratch and record it, but it takes way too long. So the GIF loader is roughly 300 lines long and quite complicated. I mean, the algorithm itself isn't that complicated, but there's a lot of stuff happening. So I'm definitely not going to do this in the usual manner, because this will take way over an hour and you probably won't be following that long. So let's just do a code review more or less. You saw the main program. You know that there is a function called load_gif, which is down here. It returns the image structure and it takes a file name. Okay, so the outline of this function is as follows. We will have a couple of structs, one with the image, one with the GIF header, which is basically only a couple of bytes, one with the GIF descriptor, which tells us the size of the image, and one with the decoder state. The decoder being the function that, or the couple of functions that decompress the compressed image into normal bytes and pixels. Then we have some local state here, the file. We will open the file, and then all kind of hell breaks loose. First of all, we can see that there is the decoder being created, so the decoder state, which is a bunch of variables that we will take a look at in just a few seconds or minutes at most. And then we read in the headers. The header is only something like 6 bytes, and it will say either GIF 87A or GIF 89A. Those are the two file versions that we have, and every GIF file starts with those characters. If it doesn't, we simply quit and say, nope, this is not a GIF file. If this works, I mean, this is all just reading stuff and reading some flags into the rest of the header structure. If this works out, then we can actually take a closer look at the header, and the header stores quite a few things. Let's take a look at the type def for this. So the signature first, which is the 7 bytes here, actually 6 plus a 0 that we append so that we can do string comparison. And then next in the file comes the screen width and screen height, which is basically the size of the image, or at least of what the image should look like on the screen. For our case, it will be 320 by 200 for the VGA. Then there will be a couple of packed flags, so every bit in this byte will be a flag with the definitions up here. So all these hex values represent some kind of flag or couple of flags. Then we'll have a background color, which is also a byte, and some aspect ratio. We will ignore both for now because we don't use them actually. Yeah. So let's go back to the load GIF function. After loading the header, we can decode the flags. First of all are the bits per pixel, which you can select from the packed flags. Then from that you can derive the number of colors by left shifting 1 by the amount of bits per pixel. And if we have bits per pixels between 1 and 4, we will force it to be 4, which is 16 colors. Why? I'm not quite sure. It was in the original, probably because GIF doesn't support anything less than 16, maybe monochrome still. That's why there's a greater than 1 here. But I haven't yet encountered any GIFs that look like that. Then we will allocate the image data structure. And this is basically just a buffer. So we allocate the struct itself. We set the width and height and allocate some data, which is basically just a frame buffer. So malloc by image width times image height. Then to be sure, we set the whole region to 0 with memset. And we're good to go. The image buffer is initialized. And the next thing that might happen is that the header says, oh, we do have a color table. And if this flag is here, then there will also be a palette, basically a color table inside the GIF file. And you already know this from the VGA course or my VGA videos, how that works. So basically we just tell the file, please give us the palette with the 256 colors, RGB, so that's why there's a 3 here. We could have also written 256 times 3 is 768 and read that in. And well, then we iterate over that and store that in the image palette. The only thing that we're doing here as well is right shifting by 2, because GIF defines the RGB colors in 8-bit, whereas the VGA only has 6 bits. So we will divide everything by 4 or right shift by 2, and so we reduce the fidelity of the palette from 8 bits to 6 bits. Nothing new. Later when we display the whole stuff, we can simply use this palette then as is. Now comes a bit more weird stuff. After the header there will be a bunch of other blocks in the GIF file. GIFs consist of a lot of blocks, and we are looking for a block of type image. So every block starts with a type byte, so we will read in the type byte, which is exactly 1 byte long, and if it's equal to image block, then we will break and just display that image. A GIF file can contain many images, for example for animations. We won't support that here because we don't need it, but you can probably extend this GIF loader to work like that. But we will just do this while loop until we encounter an image block and then just display it. However, this will probably be not the first block that we encounter. There might be other blocks. So if we didn't have an image block, we will read what kind of block we have, and this is stored in a structure called GIF block. This is a very simple structure that has a label and a size. We can look at the top here. GIF block is basically just 2 bytes, label and size. And as you can see, size is only a byte, so it can't be very big. Maximum 256 bytes. So we switch according to the block label, and there's a bunch of those. Extension graphics control, application comment, plain text. So you can put all kinds of text in there. And yeah, that's it. And maybe some other unknown block. This is the default case. And everything, all this whole loop here does is it tries to skip those blocks because we don't care about them. For animations, the GIF extension graphics control might be nice because it will tell you how much time between different images, what the transparent color is, etc. But we don't care for that right now, so we skip all of those. You can have a look later in the source code if you want to understand it more closely, but it's not that interesting and not that important for the rest of the program. So at this point we encountered the image block. The image block has a descriptor. We will read that descriptor, and it again has a bunch of fields that we can take a look at, namely the image coordinates, image left, image top, image width, and image height, and some packed flags again. Let's go back down. So here we read the descriptor, and first of all we test if the descriptor again has a color table. This is the flag, which is the same as above. So the first color table that we encountered was the so-called global color table, but every image block that we encounter can redefine the color table. It doesn't have to, but it can. And if that's the case, we just simply override our image palette, just like above. If you're doing animations, you will have to store multiple palettes and set them accordingly. And then we start setting up our decoder. The decoder state stores everything that the descriptor told us, the top left corner and the bottom right corner of the image. And it also stores the Y delta, which will be used if you have an interlaced GIF. Interlaced GIFs were used back in the day so that while the GIF was loading you could already display parts of it, like a low-res version of the image. But we probably won't need it, but we can support it. If the interlaced flag is set, we simply, when we finished one scan line, we will not go to the next, but to the fourth scan line after that. And this will continue until the whole picture has been drawn, giving you, like, even after the first couple of scan lines, already a rough representation of the image. But that's also not that important for the decoding. More important is that after that we also can read the initial code size and the block size of the GIF, of the encoded GIF. We will always read according to the block size into our internal buffer, and the initial code size will be 8 or 9 bits, and the code size can grow up to 12 bits, meaning we can store up to 4095 code words in our dictionary, basically. Then we need to store a bunch of other state. First of all, the GIF file itself, because other functions also need to access it. Then we need to store a pointer into the buffer, which stores the block, the current red block. Then we need to store the clear code. The clear code, when we encounter that in the compressed stream, it means reset the decoder to its default values. And it will most often be the first code that we encounter so that the decoder initializes itself correctly. And the clear code is always the highest code of the initial code size. So usually 256, or for example, in this example here, we have 26 characters, so the clear code would be character 27. Alright, then there's also the end of image code, which signifies that we are done with decoding, and that is the code after the clear code, so usually 257 in the case of images with 256 colors. The first free code that's available, that's reconstructed during decoding, will be the one after that, clear code +2. And our currently free code is initialized with first free. Our initial code size is code size incremented by 1. And the max code that's possible, that's currently possible, is obviously 2 to the power of code size. So 1 shifted to the left by code size bits. So if our initial code size was 8, the init code size will be 9, and our max code will be 256. Alright, does it make sense? Roughly, I hope. Furthermore, we will read the image, the encoded image, actually bit by bit, not on a file system level, but in the memory. And every 8 bits we need to load the next byte, and to make sure that the load byte routine works, we initialize it this bits in parameter with 8, which forces us to load the next byte. We'll see that also in a minute or two. So we also store the current cursor position, basically, where we draw the pixel, and we start at the image left and image top. And also we need to store the pointer to the image. Alright, that's a lot of stuff. But roughly speaking, we can, here's again the definition of the decoder state. We can sort it into a few blocks here. First of all, the file and image data blocks, then the state that handles everything regarding reading the codes in before actually decoding them, then the parameters for the decoder, like the first free code, etc., plus basically two arrays which form our dictionary, the prefix and the suffix. The suffix will be the last character of the current new code word in our dictionary, and we can build everything, the whole decoded sequence, basically by combining the prefix and the suffix. Okay, and of course the whole image related parts, like the x and y coordinates in the top left and bottom right, and the delta for the interlace. So after we've done that, we can start the actual decoding process. This is a big do loop, and it will end when our decoder has discovered the end of image code. So what do we do here? First of all, we need to read the next code. So there's a Recode function which gets past the decoder state, and we will store that in code. If we encounter the end of image code, we break. But how does the read code work? Because there's a lot of magic in there. I'm thinking that we probably should take a look now, because everything else here depends on that, and as you can see, it gets called now and then. So what does the Recode function do? Let's go up. The Recode function is relatively simple. It's this here. It needs a counter and the code that we're currently having. So this is the bit by bit reading. So we loop from 0 to the code size. So if the code size is 9, we will read in 9 bits. And every time we increment our bits in and it toggles to 9, we know, oh, we already decoded this whole bit. Let's get the next one. So we will put into our temp variable the next byte, reset the bits in variable to 1, and that's it. We loaded the next byte. And then we can start reconstructing the code that's coming up next. So if the value that we just read at its lowest bit has a 1, then we can add this value to the currently code being reconstructed. And this looks probably a bit weird, but let's say our current code was already something like 1011. That was our code. And we are supposed to have a code size of 9, so we are still missing 5 more bits. We read our next bit. For example, because we had to load the next byte. And the next byte that we take is, let's say, 10101011. So that's it. The lowest byte is a 1. So we take that. Counter should be equal to 5 at this point, because we already read in 4 bits. So counter should be 5 now. Then we take the 1, shift it by 5, which will lead to this representation, and that of course will lead to this temporary code, right? And we still have 4 to go. And now what we're doing is we simply right shift the temp variable by 1, which basically kills the lowest bit. And then the loop continues. We will take this one here, which will get shifted 6 bits, and it will calculate 11011 plus the new one here, and will give us this value. Right shift again. Well, now we have a 0 here, and it will do nothing. It will, in theory, put a 0 in front of this here, but we will not have to calculate that explicitly. Right shift again, and we get this computation here. We have to left shift by 6, 7, right? Something like that. I hope that's correct. We have 1, 2, 3, 4, 5, 6, 7 digits here, and this should be 1, 2, 3, 4, 5, 6, 7, 8. That's correct. So now we already have this reconstructed. Isn't that nice? And it will continue like that. There will be a last round with this here, and finally this will be the code that has been reconstructed. 9 bits, and we're done. So that's how this works. This will return the code. Fair enough, that's pretty simple, I hope. Okay, back into the hell down here. So there is a lot, as I said. First of all, end of image code, we didn't get that. Second of all, we could encounter the clear code. If the clear code happens, we are doing the same that we did above. The free code gets reset to first free, the code size gets reset to init code size, max code depends on the current code size, and we can read the next code, store our old code variable or reinit, and then draw the next pixel. Wait, what? You're going to say, what is the next pixel function? So read code we already saw. We don't yet know what the old code variable does, but it will get important. And we have the next pixel. The next pixel, what does it do? It draws the pixels. It takes the decoder state and a color, or whatever that might be. And it will take the image data buffer plus the current x and y coordinates times width for the y, and simply write out the color variable masked with 255 because we're doing 256 color pictures. Then we're incrementing the x-coordinate, and if it's bigger than the bottom right corner x-coordinate, we need to skip to the next scan line, and I'm signifying this by printing out a dot on the console. And we're resetting the x variable to the top left x corner. Here comes the scan line interlace handling, which I'll skip because we don't need it. But the takeaway message here is to basically we will always be here in the case 0. dy will be 0, and we will just go to the next scan line. Otherwise we might skip 2, 4 or 8 scan lines. And this will decrease whenever we finished one pass of the picture. Alright, so next pixel is simple enough. Just writes the next pixel. In the clear code case, it will just write the current code that we found, because this will be in simple code, one of the 8-bit ones, which are the only ones possible as the first byte that we decoded. Now comes the complicated part. In this else case, here in this whole block, we will have to deal with compressed data. Okay, so take a deep breath. There are two possibilities. The code that we just read can either be inside of the range of the stuff before the free code. So in the very initial case, it will be something less than 256. Or it can be in the range of being bigger than the free code. In the first case, we know that we can't draw yet because we will have to continue decoding until we find a new free code. Because the encoder works in the way that it creates something new every time and will place something in the dictionary, right? So if we found a code that is smaller than free code, we know, oh, we're not done yet. We haven't fully decoded a compressed word yet. But we can already decompress what we have, and this is done by the outString variable, and it will simply take the current code and will reconstruct the string. We'll have a look at that in a second. The else case is a bit more interesting because here we know we encountered a new free code. So we again put, just like in the first case, the new byte that we encountered in the suffix table at the free code position, and we will decode it using the old code from the last read. As you've seen above, this is initialized here, and down here we will store the current code in the old code variable. However, we also know that at this point we have fully read a compressed word, and we can actually call the next pixel function again by doing this, calling this with the suffix of the new free code, which is basically just what we took from the outString function. Afterwards, we will have to put the old code in our prefix table because this is the symbol or the code, not the symbol. So outString gives us the symbol, which will be stored in the suffix, and the old code will give us the prefix that came before that, which was a code, so a compressed string of bits. And one safety feature here is if the free code is bigger than the max code and the decoder's code size is still less than 12, because so this means we have to add another bit to our code size, but we can only do that until we reach 12. Then we will do that. We will increase our code size by 1 bit and also increase our max code. So from 9 to 10 and from 512 to 1024 possible codes, for example. Okay, so now the question is, what does the outstring method? It does basically all the magic for the decompression. The outstring, oh, where did I put it? Here's the outstring. Takes the code word and the decoder state, obviously, and will have a temporary buffer with the outcode string, basically, and it will do the following. If the current code that we got passed is less than the clear code, we know that this is something from the initial alphabet or dictionary. So in our case, it will be a value between 0 and 255. We can simply draw that pixel because it's not compressed. Everything else is more complicated. We will initialize our count variable of characters that we have already reconstructed. And first of all, we will try to reconstruct the output word from back to front. Basically, this works by taking the suffix of the current code and putting that into our outcode string, basically incrementing our counter variable. Then we reinitialize the current code with the prefix for the last value of current code. So here we get the character of our current code, and here we get which code must have followed this. And this we can do until the current code reaches the clear code, because then we know we are going into the region of uncompressed codes and there's nothing left to be done here. And as a last step, we will put the last current code as well in the string. What we have done now is we have decoded, according to the suffix and the prefix table, the compressed string, but from back to front, because we only know the suffixes and we worked our way forwards and we didn't know how long the string can be, because it can basically be arbitrarily long. That's why we also put an ample 1 kilobyte buffer here. So the only thing that we need to do here is to draw it out in the opposite direction. So we do the next pixel routine over outcount by decrementing the outcount variable. And that's it. It's probably a bit hard to imagine what it looks like, but basically the suffix and prefix table will contain, so the suffix table will contain all the characters that we encountered in the input or later in the output, and the prefix table will tell us which code must have come before that special character. And that's basically, this outstring thing here is the big magic of the Lzw compression. And the only parts that are also important for this is this part here, that we fill the suffix tables in the correct way and also fill the prefix with the old code from the previous iteration. And this is all there is to it, actually. I think we don't have anything more to say here, except let's try to build this thing. Oh, it's already up to date. And let's try to run it. Source modified, rebuild, yes please. Okay, so every dot means one scan line. It will be 2.5 lines before displaying, and here we have it, our first GIF loaded. This is simply a picture of the graphics card that's in my 386. You can probably hardly make it out, but this is the GPU basically, if you can call it that, the DRAM and the other stuff. And this is 320 by 200 pixels, 256 colors. We can use that. You can load arbitrary images up to this size. There's not a lot of error handling. You will be able to crash it very easily. And as you've seen, it's actually not that fast. Let's run it again. It takes, with DOSBox set to 3000 cycles, it takes almost 10 seconds or something. Definitely more than 3 seconds. And yeah, so there's a lot of optimization, room for optimization here. I think the load byte is probably some place where we can optimize, because this will load only one block at a time, which is probably good because it doesn't take up much memory. But also the read code is pretty inefficient by doing this whole bitwise thing. But I will have to think hard about how to make that faster. We can probably inline a lot of this or rewrite some stuff in assembler. This will improve things. But for the time being, I think it's simple enough that we can understand it, hopefully. Next time I probably will want to talk about the whole stuff, splitting this whole project over a couple of source files, as I've done here, adding a project file in TurboC, because we're getting in an area where this is all already pretty large, right? And we want to make everything a game, and you probably already saw a few hints here and there what this game will be like. But there's still a couple of things to do before that. I hope you learned something here. I know this is, and I couldn't do it from scratch because it's way too complicated and way too long. I hope you still enjoyed it. You can check out the source code. I will put up the GIF loader itself and put a link also to the original code that we based this upon. And yeah, make sure to hit the like button. I would also suggest you subscribe to not miss an episode. And as I said, I hope you learned something and you enjoyed it. And I hope to see you next time. Have a nice evening.